Welcome everybody. This is the second lesson of Chapter 2, Chemistry and Measurements, and it covers sections 5, 6, and 7. Section 5 is writing conversion factors, section 6 is problem solving using unit conversion, and unit 7 is on density. So section 2.5, writing conversion factors. As you can see here, there are two tables from your book that have conversion factors. The very first one on the left has the given quantity, the type of measurement, essentially length, volume, mass, or time, and it gives you the conversion between the metric system and the US on the far right over here. And it has conversions within each, so like a kilometer, and how many meters is that? There's 1 kilometer is 1,000 meters, so on and so forth. In the US or imperial system, for example, it has 1 foot is 12 inches. Hopefully you all know that, but those conversions are there for many of them. And what's different on this one on the right is that it has temperature, pressure, and energy that are not in the first table. This one is actually at the very back of your book on the back cover. Section 2.6 is problem solving using unit conversion. And you can see here there are 4 examples that I have provided. They're not in the book or anything, that utilize unit conversions. So what these mean are just, like as the previous tables showed, how do we convert from one unit of measurement to another? Well, we need to use those unit conversions that might have been in the previous slide. So the first one there said, a pencil is 7 inches long. What is its length in centimeters? And I've already written up there what you're asked to find. 7 inches is how many centimeters? What you need to know from those tables in 2 slides ago now are that 1 inch is equal to 2.54 centimeters. That is your unit conversion, or conversion factor. Now, when you're using a unit conversion or a conversion factor, whatever you call it, these are going to always have infinitely many significant figures. All right, so now we can actually go ahead and start the problem. And I like to use this box method where I am always going to write what is given in what it would be the top left corner of the box. So as you can see, I've written here how it would look, and there's a whole bunch of jargon there, but I write the given quantity in the top left corner of this box. Below it is nothing because what we're starting with is just a number. But then we're always going to multiply it by the conversion factor. And I've written here conversion factor where we have the desired unit. And then over that, or underneath that, is the conversion factor with the original unit, the one that's going to be canceled out. In that given quantity, we can also call the measured quantity. All right. And so we treat this is a multiplication division type problem. We just treat it like a numerator and denominator. So for this problem in particular, we have 7 inches and we're asked to find how many centimeters that is. So we take 7 inches, put it in the top left corner in the numerator. It's just inches, so we don't have a unit here. You can leave that blank. And we want to find centimeters. Your answer always needs to have the desired unit in the numerator. So we want centimeters right there. Since we're starting with inches, we use the given, in this case I've given it to you, the given conversion factor. 1 inch is 2.54 centimeters, and we just put the number there. And we put The other part of the conversion factor, the one that's going to be canceled out, 1 inch in the bottom or the denominator. All right. And the way that this works going forward is that this ultimately can be written like this: 7 inches in parentheses times 2.54 centimeters, also in parentheses, divided by 1 inch in parentheses. I like to use parentheses. It makes things clearer and allows you to be probably less likely to make mistakes when using your calculator. But as you can see, whether you're using the box method or maybe a more algebraic method on the right here, the inches are on the top and the bottom. Everything is being multiplied or divided, so they will cancel out like that. And so what we get when we do this calculation, 7 times 2.54, is 17.78 centimeters, because the only unit we didn't cancel out in this calculation was centimeters. So that's what we get here. All right, now the next thing to consider is significant figures. When you look at the numbers that you were given, we have 7 inches with 3 significant figures, and we've got 2.54 centimeters, which has infinity significant figures, and we've also got 1, which also has infinity significant figures. Since this is a multiplication/division problem, we use the number with the fewest number of significant figures, which is 3. So the answer to this question must be to 3 significant figures. And so we have 1, 2, 3. And we're going to look right there. That's an 8. Since it is bigger than 5, this number rounds up to 17.8 centimeters. Problem 2 here says a student has entered a 10.0 kilometer run. How long is this run in miles? And so we have to have a conversion factor here. We do have the same one from before, where 1 inch is equal to 2.54 centimeters. And so we could convert ultimately centimeters to inches, and then we could go inches to feet, feet to miles. We could go, and we'd have to do kilometers to meters and meters to centimeters. I'm going to show that first before we do the quicker way. So first we need to have all of the conversion factors here. 1,000 meters is equal to 1 kilometer. And we've got 100 centimeters is equal to 1 meter. We have 12 inches equals 1 foot. And 5,280 feet is equal to 1 mile. So we've got 1, 2, 3, 4, 5 different conversion factors that we're going to use here. So I'm going to write this out in the box method. We are starting with 10 kilometers. So we have 10.0 kilometers right there. Ultimately, what we want are going to be miles, so you might put that there. But we don't have a direct kilometers to mile conversion. These are more, I'm only using this one here because it was used in the previous problem, and all the rest are honestly almost common knowledge. So you should be able to do that without looking up these conversions. So 10 kilometers. But what we have to go here is from kilometers first to meters, and there are 1,000 meters in a kilometer. Since we have kilometers in the numerator there, we need to get rid of it by putting it in the denominator. So 1 kilometer goes there on the bottom, and we've got 1,000 meters right there. Kilometers are going to cancel out. And now we need to go from meters to centimeters. There are 100 centimeters in a meter. So we're trying to get rid of meters, so that goes down here. 1 meter is 100 centimeters. Your meters cancel out. Now we can use the inches to centimeters conversion factor. So we want to get rid of centimeters, and there's 2.54 centimeters for every 1 inch. Centimeters will cancel out. Now we're converting inches to feet. There will be 12 inches in each foot. And now finally we need to go from feet to miles, and there are 5,280 feet for each and every mile. And your feet will cancel out, leaving you with just miles as your unit. Alright, so if you're going to rewrite this in a more standard notation of calculations, you could have it as 10.0 times 1,000 times 100 times 1 times 1 times 1, and then we're going to have miles. All of that divided by, there's nothing from there but 1 from the kilometer, 1 from the meter, 2.54, 12, and 5,280. And yes, I got lazy and I didn't write in the multiplication signs, but you don't really need to with parentheses. They're implied. We also don't really need to write in the number ones, because multiplying by 1 is not changing the value of anything. So we could just erase all that. Maybe I'll rewrite it. But if you want, in other cases where there aren't ones, you would need to write them in. But you've got 2.54, 12, and 5,280. Alright, so what this turns into, and you could do it step by step, is 10 times 1,000 is 10,000, 10,000 times 100 is 1,000,000. So you get 1,000,000 miles divided by, and then the product of 2.54 times 12 times 5,280. And that is 160,934.4. You could also write this as 10 to the 6th over that. I guess you could write it in scientific notation, but it would be 1.609344 times 10 to the 5th. 1, 2, 3, 4, 5 times you have to move the decimal. And then don't forget the miles. And so then you do the division. 1,000,000 divided by 160,000 essentially is equal to 6.213711922 miles. Obviously that's ridiculously too many numbers, so we need to look at significant figures. We have, in this number, we have 3 significant figures. We have, for all the rest of them, because they're all conversion factors, we have, for all of these, infinitely many significant figures. So your answer is going to be to 3 significant figures. So we have 6.21, there's your first 3 significant figures. We go to the next value over, which is a 3, which means we round down. And so we get 6.21 miles. And that is your answer. Problem 3 here says, the speed limit on I-20 is posted as 70 miles per hour. How fast is this in kilometers per hour? Well, in the very previous problem, we just found out the conversion between 10 kilometers and miles. So if you remember that, it's 10 kilometers equals 6.21 miles. We're converting it from miles to kilometers in this case. So I'm going to take 70 miles. Now when you see the P here, that means per. And in mathematical terms, the word per is a division. So 70 miles per each hour. We ultimately want to go to kilometers per hour. We're going to keep the hour there, we're going to keep the kilometers there, but we need to cancel out miles. Alright, so we have here 10 kilometers for every 6.21 miles. Miles cancel out and we get kilometers. Do the calculation and you get 70 times 10 kilometers per hour essentially divided by 6.21, and you get 112.7214171 kilometers per hour. Now I'll put as a side note here, if you don't use the 6.21 because, hey, that number I got is rounded from the previous example, if you use the more, I guess, precise value, you end up with a different number that could be 112.65408 kilometers per hour. And so you can see there is a pretty big difference here. I mean, it's less than a kilometer, but it's at the first decimal place, and it is different. And it's because we've introduced error by rounding. But that's the best we can do. What number do we use? Well, since I just chose, since the 6.21 was the best we could use in the previous number, that's what we're going to use here. So in reality, we would use the 112.72 blah 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 kilometers per hour, and looking at the entire calculation, we have 70 miles per hour. The significant figures for that 70 will actually be infinity because it is a known fact. The posted speed limit is 70. It's not 70.01 or anything like that. It's just 70. And the same thing goes for the one down there. It is infinity. The 10 here technically was 3. And the 6.21 is technically written as 3, but we're going to treat each of those as infinity because it is a conversion factor. So that means since everything is technically infinitely many, you can report your answer to whatever you want. It might seem ridiculous to write all of these decimal places though, so it is probably safe to just say 113 kilometers per hour, because in reality, the cops are not going to use a radar to measure 1,000th of a kilometer per hour. They're going to measure entire kilometers per hour. They might actually report it at 115 or something like that. They might round to the nearest 5, something like that. Who knows? But 113 would be good for me. Problem 4 here says that if there are 365 days in a year, how many seconds are in a year? So the conversion factors we need here are how many days in a year. First of all, there's 365. How many hours are in a day? There's 24 hours equals 1 day. Now this is calendar days. You're probably all aware that we have leap years and leap days. February 29th every 4 years, essentially. But in reality, if you think about it, it's not exact. The Earth doesn't spin exactly the way that we want it to. So it's slightly more than 24 hours in every day according to the rotation of the Earth, but we can just say this is good enough. 24 hours is 1 day. There's 60 minutes in 1 hour, and there are 60 seconds in 1 minute. Those last two conversions are definite and exact, but the days and then the hours in a day and the days in a year are things that are technically in reality not exact numbers. So what we have here, we've got our conversion factors. Now we need to just do the calculation. So 365 days per 1 year. Multiplied by the first conversion factor, we want to go from days to hours. So there are 24 hours in each day. Days cancel out. Then we need to use the next one. There are 60 minutes in 1 hour. Hours cancel out. And then finally, there are 60 seconds in 1 minute. And your minutes cancel out. So when you do this calculation, and I'm not going to go through writing it out in the standard way anymore. I'm just going to give you the answer. 365 times 24 times 60 times 60 is 31,536,000 seconds per year. Approximately, obviously. Now, if we're talking about a calendar year, again, it is exactly that many, which is a heck of a lot. As a side note, if you want to figure out how long it takes to reach 1 billion seconds, how many years is that? You would take 1 billion, which is 10 to the 9th seconds, and divide it by that. 31,536,000 seconds per year. Your seconds cancel out. You've got years left over, which will, since it's in a denominator within another denominator, it will actually go into the numerator. And when you do that, this comes out to 31.7 years. So if you've reached 31.7 years, or 31 years and 8.5 months, then you have reached 1 billion seconds in your life.